Dear students, today we are going to discuss the next chapter, and the name of the chapter, reactions of unsaturated hydrocarbons and carbon-oxygen double bond. So you know what is meant by the unsaturated compound. Compound having the carbon-carbon double bond, triple bond, carbon-oxygen double bond, such type of compounds we call unsaturated compounds. But the unsaturated hydrocarbons means compound containing carbon-carbon double bond and compound containing carbon-carbon triple bond. So mainly the unsaturated compounds means carbon-carbon double bond and carbon-carbon triple bond, as well as carbon-oxygen double bond gives the addition reaction. So what is meant by addition reaction? So reaction in which the two molecules they combine to each other and to form a single molecule of product is called as a addition reaction. When we take one simple example, and when you take this is a compound containing carbon-carbon triple bond, it is the alkyne, and this alkyne is unsaturated. Alkyne is unsaturated, and in case of alkyne, this carbon having sp hybridization. But when we add the reagent XY and then we do the addition reaction, and when the addition reactions takes place on alkyne, then one molecule of reagent is added to the carbon-carbon triple bond and we get your product. What happened in this case? Then again, second molecule of reagent we call the XY is also added to the alkene. This is a alkene. Here there is a carbon having the sp2 hybridization. Again the second molecule is added, second molecule of reagent is added to the alkene, and then there is a formation of your compound and we get such a type of compound, and this compound we called alkane. And in case of alkane, the carbon having sp3 hybridides. So this is a simple one example of the addition reaction. And what happened in case of addition reactions? So you take first the alkyne, it is unsaturated, the carbon having the sp hybridization, XY is a reagent and it is added to the carbon-carbon triple bond. The first molecule or one molecule is added, then we get the alkene. And the second molecule is added into the alkene, then we get alkane. So what happened when we see this reaction, then we notice that in case of addition reaction, the degree of unsaturation is decreases. Means when we take a alkyne carbon-carbon triple bond, after addition we get a alkane, the degree of unsaturation is decreases. After the addition of second molecule of reagent XY to the alkene, then there is formation of alkane. So we start from the unsaturated compound, but we end up with that is a saturated compound. So we remember in case of addition reaction, the degree of unsaturation is decreases. So when you take different examples, we take a carbon-carbon triple bond, we take a carbon-carbon double bond, carbon-nitrogen triple bond, or there is a nitrogen-nitrogen double bond, or we take a carbon-oxygen double bond. So all is unsaturated compound, and this unsaturated compound gives the characteristics addition reaction. So that is the important point. Then in this case we remember, or in this chapter we mainly discuss the reactions of carbon-carbon double bond and reactions of carbon and oxygen double bond. because all that compounds give the addition reaction, but in this chapter we focus on the addition reactions of carbon-carbon double bond or triple bond and the addition reactions of carbon-oxygen double bond. So that's why we think about the carbon-carbon double bond. And when we see, this is carbon-carbon double bond, this is your carbon, this is suppose we call these two groups is there, and we know this is a pi bond. So this is the structure of carbon-carbon double bond. So what happens in case of the carbon-carbon double bond? It contains the two bonds. One is a sigma bond, second one is a pi bond. And what happens in case of the sigma bond? There is a coaxial overlapping between two carbon atoms. But when we think about a pi bond, there is a lateral overlapping. And we remember the sigma bond is more stronger, pi bond is weaker. Because in case of the pi bond formation, the lateral overlapping takes place, and lateral overlapping is weaker than the coaxial overlapping. Then we remember in this case the pi bond. What happens in case of the pi bond? The electron density lies between above and below the plane of these two nuclei. Means this is the electron density of pi bond. It is lies below the plane. It lies also above the plane. So that's why pi bond is a weaker one, and that's why these reactions of carbon-carbon double bond gives the addition reaction. But what happens when we think about addition reaction? The one pi bond is break. So what happens in case of the addition reaction? One pi bond is break and there is formation of a two sigma bond. Means one pi bond is break and there is a two sigma bond formation takes place. And we remember pi bond is weaker, sigma bond is stronger, one pi bond is break and formation of two sigma bond. So energetically this type of addition reactions are favorable. But we take an example of double bond, then what type of reagents is added to the carbon-carbon double bond? So that's why we remember it having the electron rich species, pi bond or pi bonded electrons are loosely held between these two nuclei, and it is easily given to the species which seeking the electrons or which is electron deficient. So that's why carbon-carbon double bond gives the electrophilic addition. And the question is arise why the carbon-carbon double bond gives the electrophilic addition, because pi bonded electrons are loosely held and these electrons are easily given to the species which require the electrons or easily given to the electrophilic species, and that's why carbon-carbon double bond gives the electrophilic addition. So we see the so many examples of carbon-carbon double bond, and this carbon-carbon double bond is act as a Lewis base. As like a nucleophile, it donates the electron to the electrophile and then the addition reactions takes place. There are so many examples of addition reactions. Means addition of halogen, addition of water molecule called the hydration, addition of HX means the hydrohalogenation, or the ozonolysis, all that examples which is related to the addition reaction. So we see some examples, and the halogenation. What happened in halogenation? The addition of X2 means iodine, bromine or chlorine. We take one simple example, and here suppose the addition of Br2 takes place in inert solvent, that is the carbon tetrachloride, and then there is a formation of vicinal dihalide. So this is the example of the addition reaction to the carbon-carbon double bond. These reactions we call the halogenation. any X2 means the either you take a Br2 or you take a Cl2 chlorine, they are added to the carbon-carbon double bond. In presence of inert solvent like a CCl4, we get a fissional dihalide. You take a next example and hydrohalogenation. In case of hydrohalogenation means HX, hydrogen and halogen, they are added to the carbon-carbon double bond. Such reactions we call hydrohalogenation. Similar starting compound you take, suppose they are added to the HCl, and then the addition reactions are takes place and we get alkyl halide. And this type of compound we get. So this is some examples of addition reactions: halogenation, hydrogenation. Suppose we take the example of addition of water molecule, and when we take same example or starting compound, water molecule is added in presence of concentrated H2SO4, we get here the alcohol. So all are the examples of addition reaction to the carbon-carbon double bond. Then once you see this general part, then we will discuss some reaction addition reaction to the carbon-carbon double bond, and first we discuss hydrohalogenation reaction. Hydrohalogenation. And when we think about this hydrohalogenation reaction, let us consider the addition reaction of this propene to the HCl. This is simple example. We take a propene, then this is acidic reagents or HCl. We take in presence of CCl4, carbon tetrachloride. We get this is the major product, and we get the alkyl halide. So this is simple example. But when we think about the mechanism of this reaction, and what happened in case of the mechanism? So this mechanism of these reactions having two steps. So step first, formation of carboketine. And in case of addition of the HCl, or we call the hydrohalogenation, these reactions having the two steps. The step first, formation of carboketine. So how the carboketine formation takes place? And we remember this is the HCl is your reagent, this hydrogen having the delta positive charge and chlorine having the delta negative charge. We already discussed this carbon-carbon double bond, it acts as a Lewis base. This electrophile is first approached or added to the carbon-carbon double bond, and there is formation of a carboketine. So how the carboketine formation takes place? So we write like that in first step, and there is a formation of carboketine. And once the carboketine formation takes place, and we get the nucleophilic species, that is Cl minus. So this is the first step. In first step, this is an electrophile. This is a H delta positive charge. This hydrogen having this hydrogen is added to the carbon-carbon double bond first because it is a electrophilic in nature, and there is a formation of a carboketine, and we get a Cl minus. We remember in this case, your alkene is unsymmetric one. Then there are the two probabilities. There is two product formation takes place. I write just here the major product, but along that one minor product formation is also takes place, and this is a minor product. So which product is first product is major, but why this first product is major and why the second product is minor, we will discuss later on. But we see the mechanism. So this is first step, and in first step the formation of carboketine. How the carboketine formation takes place? This electrophile is added to the carbon-carbon double bond first and to form the carbocation. Once the carbocation formation takes place, then what happens in second step? And second step is attack of nucleophile attack of Cl minus on carbocation. So this is second step, and there is your carbocation is there, your reaction mixture having the nucleophile Cl minus. The Cl minus is attack on this carbocation, and there is a formation of your product. This reaction is a fast one, this reaction is a slow one, or the first step is a rate determining step, and finally we get this product. I write here the major product. So this is simple mechanism. Step first, carbocation formation. Step second, Cl minus or nucleophile is attack on carbocation, and there is a formation of a product. So this is a simple example of hydrohalogenation. But we remember some examples, or see some examples. We take suppose this is your symmetric alkene. You take this is the unsymmetric alkene, and then in both the cases we do the addition reaction. And when we do the addition reaction, in case of this, there is only one product formation takes place. This one. Either this chlorine goes to here or either chlorine goes to this carbon, there is no difference, so we get only one product because your alkene is symmetric in nature. When your alkene is asymmetric in nature, then we get it two products. We write this Cl, and in this case this is your major product, this is your minor product. So we remember this symmetric alkene only one product after addition, and symmetric alkene after addition we get two products, one is a major and second one is a minor. So this major product is according to the Markovnikov addition. So why this product is major? It is described by the Markovnikov. This is a Markovnikov rule. We call Markovnikov rule or Markovnikov addition. What is meant by the Markovnikov addition? You take a propene, addition of HCl. This product is major, this product is minor. And this major product is according to the Markovnikov rule or Markovnikov addition. And what is meant by the Markovnikov addition? In case of addition reaction, the negative part of the reagent which is attached to the carbon, olefinic carbon, which carries the less number of hydrogen atom. And this rule we call the Markovnikov addition. We take this hydrogen, it is a delta positive charge, chlorine having the delta negative charge. Which is the negative part of your reagent? Cl minus. And ultimately, according to the Markovnikov addition, the negative part of the reagents means Cl minus, which is attached to the carbon which carries the less number of hydrogen atom. Which carbon? The olefinic carbon. So this carbon having the one hydrogen, this carbon carries the two hydrogen. This negative charge species means chlorine goes to this carbon, then this product is a major and other product is minor. So the Markovnikov addition is nothing but the negative part of the reagents which is attached to the olefinic carbon which carries the less number of hydrogen atom, and this rule we call the Markovnikov addition. So the addition of PSCl is according to the Markovnikov addition, and that's why we get 2-chloropropane as a major product. But we remember in this case, and we already explained, in case of the addition reaction there is formation of a carbocation, and when the carbocation formation takes place, we know the stability tertiary carbocation is more stable than the secondary and then the primary. Means what happen when we think this, or when we think about this reaction, then in case of addition reaction, carbocation is formed. Tertiary carbocation is more stable than secondary and then the primary. Then why tertiary carbocation is more stable? Because what happened in this case, in case of the tertiary carbocation, electron donating, when the electron donating groups, they are attached to the carbon, then the carbocation stability is increases. That's why when the electron donating groups are attached to that carbon which carries the positive charge, then the dispersal of positive charges takes place, and in such case the carbocation stability is more and more. Then when there is a more and more alkyl group is there, then the stability of that carbocation is more, as well as this carbocation is stabilized by the hyperconjugation. So that's why we remember, when there is a tertiary carbon and which having the electron donating group, then the carbocation stability is more. When the secondary carbocation, because the electron donating group is decreases, so ultimately its stability is decreases, and primary carbocation is less stable. Then what happen? Why in case of the Markovnikov of addition, which product is measured, we already discussed, and in this case we take some simple example and we will discuss this one, HCl, and what is the probability? There is a 2 probability after addition of this, and there is a formation of this carbocation in first step, and what is the second probability? Formation of this carbocation. It is secondary one, this is primary one. And which product is measured in this case? This one. This product is measured, this product is minor. And when we discuss, according to the Markovnikov addition, when this is the first step, formation of carbocation, then attack of Br Cl minus, we form the 2 chloropropane as a major product. And why this? So that's why we see the one simple example. This is a potential energy, and we write this one. We take this simple example. And what is your starting compound? It is alkene. This propene there reacts with the, suppose we call the HCl. What happened here? And we write here the progress of reaction. When this energy is called E activation, this energy we call E1 activation, and when the secondary carbocation is formed, then this much amount of energy is required. When the primary carbocation is formed, then this is the excitation energy. So what happens when you take a propene? In case of first step, there is a formation of 2 products, secondary carbocation and the primary carbocation. And we remember, when we prove by the energetic way, or energy from this energy profile diagram, this is your starting compound, they are treated with HCl, then the progress of reaction is there, and when the formation of secondary carbocation, then we see this much amount of energy is required. So why the first product is measured? Because there is formation of a secondary carbocation, it required less energy to form the secondary carbocation, and rate of reaction is more. But when such type of second compound formation takes place, then it requires more and more energy, because secondary carbocation is more stable. So secondary carbocation is more stable, it requires less energy to form this, and when the primary carbocation is there, it requires more energy to form the primary carbocation, and ultimately, according to the Markovnikov addition, this product means 2 chloropropane as a major products. Because when we want to form the 2 chloropropane, then we get a secondary carbocation, it is more stable, when we get one chloropropane, we get a primary carbocation, it is a less stable. So this is a justification for the Markovnikov addition. Then what is the support for this mechanism? Means addition, in case of the addition of HX, there is a formation of a carbocation. But what is the support for mechanism? That is a rearrangement. Means what happens when we take simple example. We take 3,3-dimethyl, that is 1-butene. We take this starting compound, and when we take this starting compound and then we treat in HI. When this compound we treat in HI, then the addition reactions that takes place, and which type of major product formation takes place? We get this is the major product. Suppose we got the A. Again we got a B product. Which type of B products? I write here. This is B product. This is major. This is minor. This product is major according to the Markovnikov addition. But what happened in this case? We remember what is the intermediate formation takes place here? We form the carbocation. In first step, formation of a carbocation, and which carbocation is formed here? Secondary. And when the secondary carbocation is formed, then we get this type of product. I write the major product, but when the primary carbocation is formed, then we get this product. So here we get two products, A and B. But we remember we get another unexpected product rather than A and B. The another third product formation takes place, and why this? Because this is secondary carbocation and the methyl shift is there, and after methyl shift, this secondary carbocation is converted into this type of tertiary carbocation. And when this tertiary carbocation formation takes place, then after this is I minus, their attack here, and we get this type of another product. And we remember this product, this is your rearranged product. Or we called unexpected product. So why this product formation takes place? Because here we get a rearrangement. And why the rearrangement takes place? Because there is formation of a carbocation. So we remember the addition reaction of carbon-carbon double bond with HX or hydrohalogenation reaction, it gives the rearrangement. And when the reaction gives the rearrangement, then ultimately there is a formation of a carbocation. And once the carbocation is formed, then the rearrangement takes place. It proves that in addition of HX to the carbon-carbon double bond, there is a carbocation intermediate formation takes place. And when the carbocation intermediate formation takes place, then only the rearrangement takes place. So that's why addition of HX to the carbon-carbon double bond gives the rearrangement, and it indicates that the carbocation intermediate formation takes place in the addition of carbon-carbon double bond to the HX.